So let's say S is the source emitting waves and O is the observer that is receiving those waves. Let V be the speed of the wave in the medium. So as if S and O are both at rest, if S continues to emit and waves in 1 second, then these waves will travel to O, so that O receives the same number of waves as S is emitting in 1 second. So if the source and observer are stationary, the observer will perceive the frequency to be the actual frequency of waves emitted by the source. Let's assume that it takes about a second for the wave to travel from S to O. That means this distance right here represents the distance traveled by the wave in 1 second, which is simply equal to V. So now if the source is actually moving forward with a certain velocity, which let us say is indicated by US, so US is the speed of the source. So now what happens is the source emits the first wave here, but as it is emitting the waves, it continues to move forward. So at the end of 1 second, let us say it's here, the distance traveled by the source in 1 second will be speed times time. So this is going to represent US. So the last wave is going to emit at this point at the end of 1 second. So you will have all the waves crunched up in this shorter distance. So you can see clearly that the wavelength of the wave as perceived by the observer has now decreased. And since the wavelength has decreased, that will cause an increase in the frequency. So let's calculate what this new wavelength is. So if F be the frequency of the source, that means the source emits F waves in 1 second. So because the source at the end of 1 second is at position S prime, all the F waves are going to be compressed in this distance S prime O, which is nothing but V minus US. So we can find this new shortened wavelength lambda prime as simply the distance V minus US divided by the number of waves present in that distance. So this gives us the length of one wave, which is the new wavelength. So lambda prime equals V minus US divided by F. But I want to find the new frequency as perceived by the observer, and we know that V equals F lambda, so V is lambda prime times F prime. Because the speed of the wave as perceived by the observer does not change, so therefore I can write F prime is V over lambda prime, which is V over V minus US times F. So as you can clearly see, since it is V minus V US, V divided by V minus US, this fraction is going to be more than 1, so F prime is going to be more than F. What will happen if the source, instead of moving towards the observer, moved away from the observer? In which case, you will have the waves stretched over this distance, which means the wavelength is going to increase. So therefore the frequency will decrease, which can be written as F prime is equal to V over V plus US times F. So in general, whenever the source is moving, we can write an expression for the new frequency or the apparent frequency as V over V plus or minus US times F, and we'll choose the appropriate sign depending upon whether the source is moving towards the observer or away from the observer. Now what if the observer is in motion and not the source that is moving? So let's see what happens then. So this is my source and this is my observer. So the source is emitting waves like this. The observer starts moving towards the source. Let's say the velocity is V0. And the wave itself is moving in this direction with the speed V. So when the observer moves towards the source, the wavelength does not change, but the speed of the wave as perceived by the observer, that is what's going to change. So the new speed, the speed of wave relative to the observer, becomes, in this case, V plus U0. Remember that U0 is the speed of the observer. And therefore, if this is the speed and the wavelength doesn't change, we can find the new frequency as f prime is v prime divided by lambda, which is v plus u naught divided by lambda. And substituting for lambda, we can write v plus u naught divided by v over f. So you find that f prime is v plus u naught divided by v times f. Since this fraction is greater than 1, we know that the apparent frequency is going to be more than the actual frequency if the observer starts moving towards the source. On the other hand, if the observer moves away from the source, then he perceives the wave to be coming slower at him, in which case we can write f prime is equal to v minus u naught over v times f. Or in general, whenever the observer is moving, the frequency can be calculated as v plus or minus u naught over v times f, and you will use the appropriate sign depending upon whether the observer is moving towards the source or away from the source. What if we have a situation where both source and observer are moving? We just have to combine the two equations and simplify them into one, which means your f prime will simply be v plus or minus u naught over v plus or minus us times f. And an easy way to apply these two equations is, remember that if this is your source and this is your observer, so remember, if the observer is moving towards the source or the source moving towards the observer, then the frequency becomes greater. If the source is moving away from the observer or the observer is moving away from the source, the frequency becomes smaller. So we use the appropriate sign depending upon the motion of the observer or the source relative to the other one.